Okay, this is the 2004 BC Free Response question from 2004. So I'm taking a look at this, and I see it's a population. It's modeled by a logistic differential equation. So they give me the differential equation, and then it looks like they're asking me for the limit as t approaches infinity, given two different initial conditions. So whenever I see differential equations, I kind of write down those general equations just to kind of remind myself what I'm looking for. So remember, in our general equations, you have the change in population over time, and you're looking for a constant times p, and then in parentheses it's going to be 1 minus your population there over an L. And that L is going to be really important because that's going to be your carrying capacity. And there we go. And so then here, that L shows up again. And that L, that carrying capacity, is going to be the horizontal asymptote that's guiding the behavior of the function. So I rewrote this equation with just the 1/5 kind of factored out by itself so that I realized that was my K. And then over here, you have your L value as 12. So when I went to go answer part A, at time 0, the initial population was 3. So I kind of sketched in a logistic curve here with a horizontal asymptote at 12. Because that's my carrying capacity. And this logistic, we know, has that initial condition of time 0, 3, and we know it's going to kind of increase till it hits there and then, approach that horizontal asymptote. So, as you approach with this first one, the HA is going to be 12. And then you have to take a look at what happens if your initial condition was 20. Well, think about this. If your initial condition was 20, but this, population model was only designed to support 12, well, then you're going to be decreasing pretty quickly until you hit that carrying capacity. An example of this would be if there was a lake that was stocked with fish, but they maybe overstocked it. The lake was only big enough to maybe support 12 fish, but they threw in 20. Well, then there's not enough food for those other fish, so then a bunch of them are going to have to die until you kind of, approach this horizontal asymptote. So the answer to part A is 12. And again, the answer is going to be 12 regardless of what your initial condition is. That limit as t approaches infinity is asking you if there's a horizontal asymptote guiding the behavior of this function, aka what is the carrying capacity. Okay, in part B, they're saying if at time 0 the population is 3, for what value of p is the population growing fastest? So there's kind of two ways you can think about this. I know in class I had said it's growing the fastest at the point of inflection, and that's going to be where L, your carrying capacity, divided by 2. So you could have just done that and said 6. If you're curious as to why that works, remember, your point of inflection occurs when the second derivative equals 0. So what you can actually do is go back up to this first derivative that they gave you. Oops, I got to scooch up. So you can go to this first derivative that they gave you, and then you can actually take the derivative of it. So I took this p over 5 and distributed it. So now I can take the derivative of that. So if you take the derivative of that, just remember that's going to give you 1/5, right? The derivative of this part is just 1/5. The derivative over here is going to be, 2 over 30. So it would be 2 over 30 p. Oh, I'm sorry, 2 over 60, which will reduce to 1/30th. So you get 1/5 minus 1 over 30 times p. Okay, and I'm going to put my p in the numerator. Then from there, you want to know when that equals, you solve that for p. Okay, so you can go ahead and solve that for p. And we're going to, when you take the derivative, we'll set that equal to 0, then solve for p. So move that over, so then you're going to have p over 30 equals 1/5, and then 5p equals 30, and sure enough, p equals 6. So again, the faster way is just to know that it's growing the fastest at the point of inflection, which is going to be where the carrying capacity is divided by 2. That'll be where your point of inflection occurs. So that's how you would do part B. Keeping in mind the split of points for this question, part A was worth 2 points, part B was worth 1 point. So if you've gotten that far, you've earned 3 points. And next comes part C, and that's where you're going to get the bulk of your points. It's going to be worth 5 of them. And so we'll kind of go ahead and tackle part C next. I'm debating on whether I should have enough room. All right, I guess we'll start it here. Okay, for part C, they are saying that some different population is modeled by, looks like a very similar equation that they gave me. Okay, I can kind of scooch it up there. So it's really similar to the other one, but they want me to separate the variables here. And we're trying to come up with an equation that's like a y equals equation to model it. So my goal is to take this differential equation and turn it into an equation that will model the population at any time. So what I'm going to do is probably start off by multiplying both sides by dt. Okay, so if I multiply both sides by dt, I'm going to get dy equals 1/5 y minus 1, parentheses 1 minus t over 12 dt. Okay, so multiply both sides by dt. And so the technique of separation by variables means you want to get all your y's on one side and all your t's and dt's on the other. So y's and dy's together, t's and dt's together. So then from here, I'm going to divide by y. So I'm going to get dy over y equals, 1/5, parentheses 1 minus t over 12 dt. And if you wanted, you could go ahead and distribute that 1/5 if you wanted to, so that you can have t, and then 5 and 12 is what, 60. So we get that dt. And here, I'm just going to rewrite this as 1 over y dy there. Okay. So now that I have my y's and dy's together, my t's and dt's together, I can go ahead and integrate with respect to each side, right? So I'm going to integrate here and integrate this side. Okay. Recall that the integration of 1 over y is going to be ln, absolute value of y. And since we're talking about population, we're going to assume that that's going to be a positive, so we'll be able to drop those absolute value bars in just a minute. And then over here, we have to integrate each piece. So when you integrate on this side, okay, you'll tack on a variable, add 1 to the exponent, tack on a variable. So you'll have 1/5 t minus t squared. Again, dividing by 2, that's going to turn that into a 120. And we're going to say plus c. Again, technically there's a plus c here and over here. We're just going to write it on this side. Okay. So you get to this point, and now we're like, all right, we have the ln of y equals all that, so we need to solve for y. So to solve for y, I would probably e both sides, right? So I'm going to e over here and e that part there. And we know that e and ln kind of cancel each other out, and we're going to say y equals, and again, we can drop those absolute values because your population is going to be positive. And then you've got this kind of a mess over here. So I would probably rewrite it. I'd say e to the t over 5, right, minus t squared over 120 plus c. So we're going to kind of use that same rule that we were. Our goal, remember, is to rewrite that as something so we can get e to a power times e raised to the c. So we're going to say y equals, we'll still have this part, over 5 minus t squared over 120 times e to the c, okay? And then we're going to take this, e to the c, and say that's some other c value. Okay, that's some other c value. So my equation is going to be y equals c, right? E to the c is just some c, e t over 5, raised to the t over 5 minus t squared over 120. Okay? So I'm not quite done yet because I have not applied my initial condition. Okay, but I got to flip over to the back. So there's an equation that models the population, but I still need to figure out what c is, and we're going to find c by applying the initial condition. So I'll pause it. Okay, so we had our equation here that had a c. So in order to get it, just to be a y equals equation where t is the only variable, I want to solve for c. So you do that by applying your initial condition. They said here that at time 0, the population was 3. So I take that 3, I plug it in for y, and then I take t equals 0 and I plug it in there. And we know that e to the 0, 0 minus 0 is 0, and e to the 0 is 1. So essentially that tells us that c equals 3. So my final answer, my final equation is going to be y equals 3, there's that c, e to the t over 5 minus t squared over 120. And if you got to there, you should have earned all 5 points. All right, and for the last part, so the very last part of the equation, it says for the function of y found in part C, so for this guy right here, what is the limit as t approaches infinity? Okay, so basically part D here is asking for the limit as t approaches infinity for this equation, okay, for 3e, right, so for this thing here. And normally when we see the limit approaching infinity, for a logistic equation, we always think about that carrying capacity. But with this new equation, that's not the setup I have here, right? Like I don't have a carrying capacity here. So you have to kind of think of it, you have to kind of, use logic and think your way through it. Okay, so I just kind of wrote down the equation from the front there so I didn't have to keep flipping. So this is what they gave me. And so if you tried to plug in here, you'd end up with like an infinity minus an infinity and e to the infinity. That's kind of one of those indeterminate forms. We don't really know how to deal with those yet because you don't know L'Hopital's. If you do know L'Hopital's, you can go ahead and use that to get through here. But if not, I want to remind you of that differential equation from the front. And we can tell here that if your t value is between 0 and 12, your dy, the overall quantity, is going to be positive, because if this is, say a 6, right, 1 minus a half, that'll be positive. So you'd get a positive here, and that means that the population is going to be growing, right? If your dy dt is positive, that means your population is growing. But if you're saying that t is approaching infinity, that means your t is going to be a heck of a lot bigger than 12. And if you plug in a number here that's a lot bigger than 12, okay, then you're going to get 1 minus something that's bigger than a 1, right? Because, a million or whatever divided by 12, 1 minus that's going to be a negative. So that means that your population is going to be, your change in population is going to be negative, and that means, right, that implies that your population is going to be decreasing, okay? And since we know that our initial condition, decreasing, we know that our initial condition, our population started out at 3. So if you started at 3 and you're going to be decreasing really fast, and your population obviously has to be positive, you can say that this thing is headed towards 0. Okay? We know that our population started at 3. This tells us that it's going to be decreasing right here. Population is decreasing. And if you started at 3 and you have to decrease, and we assume that your population has to stay positive, that means you're going to be heading to 0 as t goes to infinity. And I think that was only worth 1 point at the end there. So hopefully you were able to get a bunch of points out of the 9 available. Have a great day.